This is the signal integrity getting started for HFSS version 9. In this example, we will solve a fairly simple structure designed to demonstrate several ideas common in signal integrity type problems. The use of terminals, differential transmission lines, time domain reflectometry in HFSS, full wave SPICE model export, and time domain analysis in Maxwell SPICE. As this is the third getting started example and covers some more advanced topics, many basic topics will not be covered in detail. It is assumed that the user has already reviewed the waveguide T-junction getting started as a minimum. If you have not reviewed the T-junction getting started material, please do so now before continuing in order to be familiar with the basic concepts of HFSS. Begin by starting HFSS 9 and inserting a design. Use the file Save As command to save the project as stripline pair. Change the solution type to driven terminal in order to specify specific excitations on each line as opposed to modes at a wave port. This type of excitation is commonly used in multiple transmission line signal integrity type structures. Also, verify the units are set to millimeters in the 3D Modeler Units menu. Rather than create the model in the normal fashion, we've placed a script on the CD that contains this video. If you select Tools, Run Script, select SI Model Creation, VBS, the software will load in and execute the Visual Basic script used to design or to create this geometry. This type of scripting can be created using the record script anytime the HFSS is used. You can see here what the script has created is a substrate, an error object, trace 1, trace 2, a ground plane on the bottom of the structure, and a ground on the top of the substrate with a hole in it, as indicated. Once the geometry is created, we move on to setting up the boundaries and excitations. The first boundary to be used in this project will be the radiation boundary. If the object air is not selected, it needs to be selected now. Once the object is selected, we use the HFSS Boundaries Assign Radiation menu to assign a radiation boundary to the open surfaces of the air box. We can use the object selection here since the bottom face is coincident with the ground conductor and is shielded by the perfectly conducting object. Otherwise, we could use face selection, select the 5 faces requiring the boundary, and assigning radiation to only those faces. The ports are the only remaining part of the model that must be specified. There are many ways to specify ports in a simulation, and this topic is covered in detail in the online help provided with your software. In general, wave ports should be properly sized to capture the fields for particular signal modes, and the port should be placed far enough away from discontinuities to ensure a uniform cross-section in the structures and fields. In order to assign ports, we will take advantage of several aspects of HFSS 9. The drawing plane specification, which we'll set to YZ, using an object to specify a boundary, and copying a boundary along with an object. After we've set the drawing plane to YZ, we go to the pull-down menu to Draw Rectangle, and in the bottom of the screen, we'll enter the coordinates for the rectangle, 20, -4, and -1 for the first point, and for the size, 0, 8, and 2. When we hit enter, we get the properties panel up, we select the attribute tab, and we name this object port 1. And you can see it's shown up in the model tree. While this object is still selected, we choose HFSS, Excitations, Assign, Waveport to begin assigning the port boundary to this object. We change the number of terminals to 2 and click Update. We then select New Line under each terminal to specify a terminal line, the first being at 20 minus 0.9 and minus 1, with the second vertex at 0, 0, and 0.95. When we hit Enter, we get the terminal line, and we do the same thing for terminal 2 on that port. The terminal line for port 2 spans from 20, 0.9, minus 1 to 0, 0, and 0.95. Again, when we hit Enter, we have the new line defined, and we hit Next. Now we select New Pair to specify a differential pair of terminals, and you can see that the default impedances of 100 ohms and 25 ohms are set for the differential and common mode, and we'll keep those. We select Next, and the single-ended impedances are set to 50 ohms. Again, we'll accept that default and finish the terminal setup. Now that the first port is specified, we will copy the object along with the wave port and terminal line specifications, saving quite a lot of keystrokes in the process. First, we make sure the duplicate boundaries option is enabled in the Tools Options HFSS Options menu. And here you can see duplicate boundaries with geometry is indeed checked. We dismiss the panel, and we can first we need to make sure that the object is selected. Go to the model tree and select port 1. There we go. And now we can duplicate along a line, and we'll enter 20, 0, and 0, and for the vector minus 40, 0, and 0, and we'll tell it we want a total number of 2, and click OK to complete the process. And you can see we now have 2 fully specified wave ports. The next step to complete is to set up the solution parameters. We'll add a solution setup by clicking on Analysis. Tell the software we want to use an adapt frequency of 8 GHz and a maximum number of passes of 10, with a maximum delta S per pass of 0.101. And we'll select all the remaining options as default, and we're ready to click on Analyze. Once the solution process is started, we can view the progress by selecting Profile, Convergence, or Matrix Data under Setup 1 in the project tree. As you can see, I've jumped ahead to the completed solution. This took approximately 8 minutes on the Pentium 4 the problem was solved on. It would take more or less depending upon the speed of your machine. Now that the simulation is complete, let's review the results. We'll begin by reviewing the matrix data under Setup 1. The S11 for the differential mode is significantly smaller than for the common mode. There's the differential mode, S11, and there's the common mode. And this is correct since the return path for the differential mode is on the adjacent trace and is largely unaffected by the hole in the plane, whereas the common mode return is through the planes and the return current is directly affected by the presence of the hole. If we select Z0 and scroll to the right, we see the trace impedance for the common and differential modes. Notice that the trace impedances are very close to the source and load impedances that were specified during the terminal setup, 98.19 and 28.4. We'll dismiss the panel and we'll move on to examine a field plot. Before we set up a field plot, we want to make sure that we have the source excitation set correctly. So we'll go to the HFSS Fields Edit Sources menu and set port 1 terminal 1 excitation to 1 volt. As you can see, it's already set that way as a default. And we'll set port 1 terminal 2 excitation to 1 volt. But we'll specify the phase as 180 degrees. For port 2, we simply want that port to be terminated. So we'll select terminated and accept the 50 ohm resistance by default. Click OK. We want to plot on the YZ plane, so we'll go to the model tree under planes and select global YZ. Then we'll move to the project tree and click field overlays, plot fields, and we want the complex mag-E plot, and we'll simply click done when the panel comes up. And in just a second we get our plot. I'll hide the key here so we can see a little better. And I'll also rotate this around so that we can see it edge on. And as you can see, the high field is in the area between the traces as expected for a differential line. In order to get a SPICE file output to represent the structure and simulate in the time domain, we need to set up and solve a frequency sweep. We'll go back to the project tree under Setup and add a sweep. And we're going to select an interpolating sweep with 0.008 gigahertz as the start frequency, 8 gigahertz as the stop frequency, and 0.008 gigahertz as the step size. We also want to check the extrapolate to DC box to get the correct low frequency response and set the snapping tolerance to 0.1. At this point, we select OK and we run the sweep. Again, we'll jump ahead to the completion of the simulation. It took approximately 18 minutes on this Pentium 4. Again, your time will vary depending upon the speed of your computer. Once the analysis is completed, we can review the results again. First, we want to create a report to review the S parameters. And we select both the differential and common mode S parameters. S11 common and S12 common. Add traces. Done. And you can see the S parameters. Again, you can notice that the differential S11 in blue is much lower in general than the common mode S11 as represented by the green line. Another method of viewing these results is to use the time domain reflectometry function built into HFSS. First, let's assume that the loads are perfectly matched. In order to set this up, we select Wave Port 2 and then Properties. Under the Differential Pairs tab, we now enter the impedances that we got from the previous analysis, 98.2 and 28.4 for the differential and common modes, respectively. And after we reanalyze to allow the software to do the post-processing, we'll go into the report generator and we'll select time as the domain, and under TDR options specify 7e to the minus 11 seconds for the rise time and 1 nanosecond for the maximum plot time. We'll select the S parameters of interest. We want the real parts. Add trace. And when we select done, we get TDR plots. Due to the narrow frequency range of the simulation, we have minimal resolution in the TDR plot. However, the discontinuity in the common mode signal is clearly visible and is clearly minimized in the differential plot. A detailed discussion on TDR is beyond the scope of this tutorial. However, the process for creating TDR data is consistent for more complex structures with wider bandwidth simulations. For now, we'll close the TDR plot and move to the topic of exporting the solution data to a SPICE model for further time domain simulation. Since SPICE is a terminal-based simulation system, we will want to switch the excitation mode to single-ended before exporting a SPICE circuit. To do this, we select Excitations, Waveport 1. In the project tree, we go to Excitations, Waveport 1, Properties, and go to the Differential Pair tab. We'll select the differential pair that we set up and remove it so that we have only the single-ended excitation. And of course we have to repeat the same procedure for Waveport 2. Again, we rerun the analysis to perform the post-processing necessary to switch back to single-ended mode. You can see it runs very quickly. And we're ready to export the SPICE subcircuit. We move to the matrix data panel, where we can see the equivalent circuit export button. We select that, make sure we're set up for Maxwell SPICE. You can see we're going to export a full wave SPICE file. Click OK, and we now have a full wave SPICE file that represents all of the electromagnetic field simulation of this particular structure. This completes the HFSS simulation of a signal integrity structure. We'll save this project and we can click File Exit. If you would like to see the time domain simulation of this subcircuit in Maxwell SPICE, you can continue to follow along with this tutorial. Otherwise, you may end the tutorial at this point. If you have the Maxwell SPICE package, begin the SPICE analysis by opening up the Maxwell control panel and creating a new project named circuit_stripline, as we've done here. Open the new project and you should have the schematic capture window as it's shown. Begin by inserting the SPICE equivalent circuit we just created in HFSS using the Add, Full Wave SPICE, Import Subcircuit menu. In the dialog, click on Edit and select Import. You'll need to browse to the location where the full wave SPICE circuit is, in this case the same location that the HFSS project is in, and select it. Select OK. And if I select on the loaded definitions, or click on the loaded definitions, you can see the SPICE circuit loaded in. So we'll select Done. OK. And now we click in the upper left corner for placement of the circuit, and then down in the lower right. And the part is placed in the window. We'll right-click and select Done, and our sub-circuit has been added to the model. Jumping ahead, I've added some load resistors to this structure, or to this circuit, using the add resistor, add wire commands. We've put load resistors in parallel with the output, as well as a series load resistor, to provide the correct common and differential mode impedances to the circuit. The circuit topology was derived from the book High-Speed Digital System Design by Stephen Hall, Garrett Hall, and James McCall. And we recommend that you refer to this material for more information on the selection of these resistors. Now we've gone ahead and added ground connections to all of the reference terminals. And we've also added two 50 ohm 100 picosecond lossless transmission lines using the Add Line No Loss menu. We've also grounded the reference terminals for the transmission lines. We've added 50 ohm source resistors, and we've added piecewise linear voltage sources. As you can see, the piecewise linear source has 0 volts at time 0 and 1 volt at time 7e to the minus 11, so that the time domain analysis is consistent with the TDR analysis we did in HFSS. Finally, we've added two voltage probes, V1 and V2, so we can measure the signal at the beginning of the delay line. And now we're ready to run the SPICE simulation. We'll click on Solve, Run SPICE, select Transient Analysis, and we have a 1 picosecond time step set up with an output stop of 1 nanosecond, again consistent with our HFSS simulation, and a maximum step of 0. We'll dismiss the panel, select OK, and the SPICE simulation is complete. The dialog comes up and allows us the option to load all signals as default, which we will do. So we'll close the panel. And we'll use the results calculator command to look at the signal, differential signal. So we select both individual signals, copy them to the calculator stack. Then we'll add them up, and we'll load that signal back onto the loaded signals stack. Click Done. Now we can select Results, New Plot, and select the signal we just created, and OK. And there's our plot. If I change the defaults by double-clicking in the window, I can select minimum value of 1 and number of divisions of 11. And you can see this plot now looks very similar to the plot that we saw in HFSS. The exceptions being the delay line and the units on the Y-scale being voltage instead of reflection as it was in HFSS. To produce a TDR plot in the differential case, we'll dismiss this plot, go to the second terminal voltage source, and specify the volts to be -1, and we'll rerun the simulation. First we'll delete all the previous signals so we don't get confused, and we'll run SPICE again. Verify the transient analysis setup. And once the simulation is completed, we'll return to the calculator to create our signal. Again, we copy the individual signals onto the stack. This time we'll subtract since we're looking at the differential signal. Load that back in to the system. And we will plot the signal again in the differential case. And you can see, once I rescale this, that again this signal looks very similar to the case that we saw, the differential case that we saw directly in HFSS. Set this to 1.2 and OK. And once again, very little discontinuity effect in the differential case. Now we can save and exit schematic capture. Both the transmission line files and the Maxwell Spice files have been saved. Feel free to experiment further to fully understand the capabilities of these tools. This completes our signal integrity tutorial with HFSS and Maxwell Spice.